Okay, class, here we are one more time, sitting in the bed in the motel room, ready to talk about a little thermodynamics here. Okay, so we're picking up where we left off at the last lecture, and we're going to vary some parameters in the Rankine cycle and see how it affects different conditions, thermal efficiency, and the operation of the steam turbine, or two of them. Remember that steam turbines don't like to have a lot of moisture in them, liquid moisture condensing. It's in the vapor state, it's all good. If it starts condensing and forming droplets, the droplets beat the heck out of the turbine blades and can cause cracking. It can hit the trailing edge and break off little chunks of material and generally cause damage. So drier steam is better for a steam turbine. So we'll keep those parameters in mind. So this is first slide, looks at the effect of varying condenser pressure. And so we're going to look and we're going to see that we've got two cycles on here. Let's see here. This is the last one. I'm getting myself together here. Okay, making sure that I've got everything in the right position. So we see that we've got the basic cycle 1, 2, 3, 4, 1, and that's with the condenser pressure at atmospheric pressure. Well, steam power plants, big ones, don't operate with the condenser at atmospheric pressure. They reduce that pressure in order to increase the efficiency and get more work out per pound of steam, more electricity generated per pound of steam. And so that's what we're showing here. We could, if we drop condenser pressure on this initial cycle, then we can run at this lower pressure right here. And this is an isobar and this is an isobar. So they're lines of constant pressure. And so we can run our cycle from 2 prime, 3 prime, 4 prime, up and over to 1 and down, okay? And so let's take a look at how all this works out. So 1 is atmospheric, as we've seen, the one so marked. And when we reduce it, then we would go down to the lower pressure. And if I push one more time, we get to see that nifty little blue line segment shift down from the higher pressure to the lower pressure. That's so much fun, we should do it again. Okay, and so notice that at atmospheric pressure, we're going to condense at 100 degrees C, which is the boiling point of water at atmospheric pressure. And so that goes together. But if we can go down to subatmospheric pressure, in US units, this is typically 1 psi A or so. This pressure goes down to about 110 Fahrenheit, which, oh gosh, I don't know. I don't do that conversion well, but 110 minus 32, what is that, divided by 1.8? So it's about 30 or 40 degrees C, which is what we would have down here. That will help our efficiency. We notice you can look at the moisture in the turbine. If we stop the process here, then we still have a good bit of moisture in the turbine. If we were all the way over here, the steam would be dry and we would have no moisture in the turbine. If we're all the way over here, we're 100% liquid, not moisture, but liquid, I mean to say. And so this is all liquid, this is all vapor. So this is a significant amount of liquid droplets in the steam flow. But if we drop pressure and come straight down, oh my goodness, the quality has gone down and we have more liquid. So just by itself, dropping condenser pressure would help efficiency and would hurt the turbine by probably incurring more damage. The other way to look at it is look at the heat rejection area. The heat rejection area is from 2 to 3 down to the axis. We don't have the letters A and B, but that area is the heat rejection for the initial cycle. And for the second cycle where we lower the condenser pressure, it's this area enclosed here. And so we see that the heat rejection decreases, so the area enclosed in the cycle increases, and the enclosed area represents the net work per cycle going around closing the thermodynamic cycle. So reducing condenser pressure is great if we can figure out how to do it. Okay, and so let's see. Okay, since the temperature, and this is the other way to think about it, I guess, in terms of thermodynamic theory, since the temperature of the heat rejection for the modified cycle is lower than that for the starting cycle, 1, 2, 3, 4, 1, the cycle condensing below atmospheric pressure has a greater thermodynamic efficiency. So if we look at that, we'll see that I'm trying to get my cursor back. These cursors go away. Well, anyway, it's not going to come back to, oh, there it is. Okay, so we see the average temperature during the condensing process. Well, it's this level, which is much less than 100 for the modified cycle with a low condenser pressure, and it's up here. So obviously the average temperature, I mean, that looks like they're constant temperatures. So it would be easy to do the average. It's just this compared to this is going to be lower in this case. The temperature during the heat addition does change a little bit because the heat addition in the initial cycle is from 4 up to the dome and over to 1, and that switches to 4 double prime, goes through 4, and then goes up to 1. And so temperature of the heat addition drops a little bit, but not as much as the condenser pressure. So we conclude that this change, this drop in condenser pressure, would improve our cycle efficiency. Okay. Condensers normally operate with steam condensing at pressure well below atmospheric. The power plants, they want to pull that. They're only making one product. They're just making electricity. Electricity comes from the energy delivered to the shaft of the steam turbine, which is coupled to the generator. And so the lower the condenser pressure, the greater the work they get out of the turbine, the more electricity they get out. And so they're going to pull that condenser pressure down as low as possible. So the heat rejection to the surroundings, the lowest feasible condenser pressure is the saturation pressure corresponding to the ambient temperature. And really, you can't get it down quite that low because you have to have a finite temperature difference to operate your condenser, which is just a heat exchanger. So if the lake water, let's put it this way, if the lake water is 50 or 60, you're going to see that condensing temperature is between 105 and 110, maybe 120. And you need that finite delta T in order to be able to buy a small enough heat exchanger for your condenser that you can afford to buy it. Okay, primary reason for including condensers in vapor power plants is to increase thermal efficiency. Realized when the condenser operates at a pressure less than atmospheric, the lower the better for efficiency. And the other part is that we can't just throw the working fluid away because this is very, very pure water. The water that circulates in these high pressure power plants is far purer than the water that we drink. The only caveat to drinking it is that it probably has oxygen scavengers and other chemicals added to it. So you wouldn't want to drink it for that reason. But the general purity of the water is far better than that comes out of our tap. Tap water has to be cleaned up tremendously, demineralized, using typically a reverse osmosis process, which are membranes that the water is forced through that filter out almost everything. As far as I know, RO water is the standard for the industry. You see industrial sites, sometimes using RO, as well as the large power plants. And so it's less corrosive, and it's not only just corrosion. Corrosion is linked primarily to oxygen, but the minerals that are left behind will form a scale on the water side of the heat transfer components that basically is an insulating scale that reduces heat transfer and will really bite you on efficiency, because you have the same temperature differences between the steam side and the hot gas side, but you can't transfer the heat because you got a layer of scale on there, which has low thermal conductivity, low K, and hence acts as a layer of insulation. So we've got to return that water. We don't really have a choice. Okay, more on condenser, varying condenser pressure. Steam condenses, energy is discharged by heat transfer to the cooling water flowing through the condenser, and that can be cooling tower water, which would be typically 80 to 90 degrees, or better yet, if it's lake water, it could be between probably 45 and 65 degrees, which is going to make your cycle more efficient if you've got the lower cooling water temperatures. It's a lot of heat that gets transferred, but because of the low temperature they're involved in the temperature of the steam condensing and the temperature of the condenser water into and out of the condenser, there's not much opportunity to recover it. If you recall from your second law analysis, low temperature energy doesn't have much potential to do useful work. High temperature thermal energy has tremendous potential. And so as we degrade that energy by taking it to a low condenser pressure, we make what we reject from the cycle pretty much worthless for any practical application. Okay, so now let's take a look what happens if we increase the boiler pressure. And so you can see on here, we've got our basic cycle, 1, 2, 3, 4, and then we have an increased pressure, which means that the heat addition then occurs from 4' up to the dome to 1'. And so that represents the increase in boiler pressure between those two cycles. You can also see what happens to the turbine. The turbine is not particularly happy because we have a lot of moisture at 2, but oh my goodness, at 2' we have even more moisture. So, this is not really going to work very well for us. So this is too much moisture, and this is way too much moisture. Of course, we see that the phase change occurs at a higher temperature. Notice the distance across the saturation dome is less, so that there's less of an amount of energy required to boil a pound or a kilogram of water at higher pressure than lower. And when you condense it, you don't get as much out. So this is kind of what the higher pressure of the boiler looks like. We can look at the areas enclosed in the cycle. So we were 2, 3, down to the axis and back for the heat rejection. The heat addition was from 4 up to the dome to 1. And the network is the area enclosed in that cycle. So we see when we increase the boiler pressure, now the pump has to take us from 3 to 4'. The boiler, the heat addition goes from 4' up to 1'. And then we drop down through the turbine. This is for an ideal cycle. And then we reject heat at the same temperature. So the temperature of the heat rejection average has remained the same. Temperature of the heat addition has increased. So this will definitely increase our boiler efficiency, but the turbine's going to squawk because it's going to incur more damage. All right. So now I'm catching up with the slides. The first one is at the given initial pressure. The other one is a higher given pressure, so we're going to increase it, and then so that shows the change. That's so much fun. So we'll go from there to there. Okay, so more on the boiler pressure increase. This shows the average temperature of the heat addition from 4 to 1 is relatively low compared to the average temperature during the heat addition from 4' to 1'. So remember, the heat is added from the point it exits the pump at 4 to the point that we hit the saturation dome in these cycles, because we're not doing any reheat yet. And that's him stating what I've already said. The average temperature of heat addition for the modified cycle with the primes is greater than that for the initial cycle. So the modified cycle, the high pressure cycle, has greater thermal efficiency. So that's what increasing the boiler pressure does, even though the turbine doesn't like it because it sees more moisture. Okay. So now he's making the point about the steam quality, which is the point about the turbine being beat up more by water droplets. So we're going to go from 2 to 2' as we increase the boiler efficiency. So there's X2 quality, still not good, but we're going to slide down to here when we increase the boiler pressures. So that's not particularly good on the turbine. If the quality of expanding steam becomes too low, the impact of liquid droplets on steam can erode turbine blades and possibly diminish performance. Absolutely correct. 100%. Okay, so Rankine cycle modifications known as superheat and reheat are additions to the cycle that can let us operate at higher boiler pressures while avoiding the low quality steam in the turbine. And another modification is a supercritical cycle, and we'll see that in upcoming slides. Okay, so this is what happens with superheat. So instead of stopping at point number 1, we're going to continue up the isobar to point 1', which is obviously well out in the superheat area. So we'll go from 1 to 1'. And then when we expand through the turbine isentropically, i.e. no irreversibilities or heat transfer or anything, we drop down here, which is a whole lot better on the turbine because there's far less moisture than there is over here. So the addition of superheat is a good thing. It also helps the average temperature of the heat addition, which helps the efficiency of the cycle. So this is kind of a win-win situation. I don't think the only negative is that we do operate at higher temperatures. See, the temperature at 1' is greater than the temperature at 1, which indicates it's more aggressive on the materials that the boiler tube and the furnace is made out of. So that's a potential downside, but to a limited extent, we can handle this. If it goes too high, then we can have issues, even today. So there's the average temperature T4 up to T1, and then there's T4 to T1', and you can tell it's obviously higher. So that's going to help the efficiency. That's the words are the higher average temperature of the heat addition, because again, heat is added to the working fluid from the point that we exit the pump up until we enter the turbine. Okay, so our modified cycle has a greater thermal efficiency. And then now he's making the point about how the steam quality is larger over here at 2' than 2, and so the turbine would really likes this. And, okay, so we're going to slide the quality box over from 2 to 2'. Okay. These changing terminology. Boiler with a superheater, he says, is called a steam generator. I don't know. In my experience, it's still called a superheat boiler, but whatever. That's fine. Okay. So another thing we can do is we can add reheat. A reheat cycle is another Rankine cycle modification that takes advantage of increased thermal efficiency resulting from high average temperature heat addition, and yet avoids low quality steam to damage the turbine. So what we do is we kind of, instead of buying one big turbine, we buy two smaller turbines. And we call one a high pressure turbine and the other a low pressure turbine. So then when we come out of the boiler, we go initially into the high pressure turbine. We expand. As the pressure drops, steam expands, turn the shaft, put power in, get electricity out, and then we get down to a point and we come back out of the turbine. And, you know, ideally this is at constant pressure, but in reality we'll have a 30, 40, 50 pound drop through here. But we go back to the boiler. We have separate heat exchangers called the reheat. Reheater sections or reheat heat exchangers or reheat superheater. Probably reheat superheater is what the power industry would call it. So we pick up a bunch of temperature, even though we lose a little bit of pressure, and we go back into the second turbine, which we're calling low pressure turbine. And so this helps us in a couple of different ways. If we look on the cycle up here, so 5 to 6 is the pump, the isentropic pump. 6 up to the dome is heating the liquid feed water to saturation, and then we're coming across and we expand up, and this is of course at our high pressure, and we go ahead and we superheat up, and then we expand through the first turbine, and this is showing us coming out still in the vapor state. We're not two-phase yet, and then at that pressure, so this is an isobar, we go back to the boiler and reheat again. Oftentimes this is all the way to T1, but they didn't draw it that way on this diagram. So then, but we're further out in superheat, and then we expand down to the exit of the turbine, which is the condenser inlet state, which means that we have less moisture here than we would have had here, and we have a higher average temperature during the heat addition than we would have had if we did not implement this reheat cycle. So reheat cycle is pretty good. It just adds pipe, it adds more hardware, adds 2 turbines instead of 1, so it adds cost to the cycle, but there is an increase in thermal efficiency. Okay, so what are we saying here? With reheat, steam quality at the turbine exit state 4 is greater than at state 4 prime. Which is the exit without reheat, and I agree with that completely. So we're going to show the quality sliding over there on the diagram. We'll go back and show that again. Okay, so that's what reheat cycle is all about. If you recall back to the initial diagrams of the TVA system, it has reheat. It has what we call regeneration, which is the feed water heaters. We'll talk about those in a few minutes. And it has the reheat cycle as well. So this stuff gets built out there in the real plants. Okay, so departures of the reheat cycle from the simple vapor cycle considered thus far include process 1 to 2. So we're going to go through the high pressure turbine stage, and then steam is reheated in the steam generator. We've seen that. And process 3 to 4, steam expands through the low pressure turbine. So I think that's should be pretty clear, I hope. So when you're doing calculations on this cycle, if you want to calculate the thermal efficiency, you got to account for both turbines and the regular boiler high pressure steam as well as the reheat steam. So the total work developed by the turbine stages are processes 1 to 2. So that's the high pressure turbine, and the process from 3 to 4, which is the low pressure turbine. So yeah, we're going to calculate the cycle. We got to calculate those, and they're independent, separate calculations. Total heat added during vaporization, superheating, and reheating are both processes 6 out of the feed water pump, to 1, which is the exit of the high pressure turbine, but we come back at 2 and exit at 3, and that's the reheat cycle, and that's additional energy that the boiler has to put in to the working fluid. So you've got to do calculations on all 4 of those processes. And so the efficiency of this cycle is the work out of the high pressure turbine plus the work out of the low pressure turbine minus the pump work. We still just have 1 pump, plus the 2 heat additions, Q dot 6 to 1, which is I'd say the main steam being generated by the boiler, plus Q dot 2-3, which is the heat added in the reheat heat exchangers. Okay, supercritical. Supercritical, ideal reheat cycle. The way this game is played is higher pressure, higher temperature equals higher efficiency, and it's a question of materials. Do we have the materials that can stand up to the required duty? So increases in those pressures and temperatures will help our efficiency, and this is what happens in the supercritical. The critical point is up on top of the saturation dome, and if we exceed that in the boiler, then it's called a supercritical cycle. So let's take a look. We got process 6 to 1, and so you see up here that, my gosh, when we boil the liquid, it doesn't 6 to 1, it doesn't go across the dome because the pressure is high enough, and of course the pump is the one that gets us to that pressure. So this is, saturation at whatever pressure, low pressure in the condenser. That's a hoss of a pump that takes us up to supercritical pressure. And then when we start heating, we just go from a liquid to a vapor, and it doesn't really boil. I don't know. It's just a change of state, but it doesn't go through a boiling process at constant temperature like we do when we're below the supercritical process. So that's that. And so that's the little ball shows that process. We'll do it again. How nice. Okay. No phase change occurs. Instead, water flowing through the tubes is heated from liquid to vapor without the bubbling associated with boiling. We'll do it again. Today's supercritical plants achieve thermal efficiencies up to 47%. Ultra supercritical plants are even higher in pressure, and they say they have thermal efficiencies above 50, and I'm sure that's true. TVA has the Bull Run plant, which has been multiple times the most efficient Rankine cycle plant in the country, if not the world. And I think the pressure runs there 4,500 psi. Critical pressure is like 32, something like 3206, 3209. I think it's 3206, but you can check that on me. But it's a little over 3,200 pounds. And so at 4,000, 4,500, you're obviously way above the critical pressure. And so that's going to help. The issue is, what's the longevity of the materials when you push them this far? So the better the material science, the better the materials for boiler tubes and power plant components, the higher the temperature and pressure can go, and the higher thermal efficiencies we can achieve. Okay, this is Irreversibilities. I think I'm going to stop here. I'm not sure how long I've droned on, but I think probably long enough to post this. So I'm going to look. I'll probably send you guys some homework problems to start working on some of this. So hope you're enjoying these. I know they're a lot of fun to make, and I'll be in touch soon. Thanks. Bye.